So hello, today we will talk about visualization of infinities in mathematical practice. And that is my co-author Karl Heuer from the Technical University of Berlin, a working mathematician and computer scientist. And I'm Dennis Arakaya, a PhD student in philosophy from the University of Hamburg. And just in general, there is a growing movement in philosophy of mathematics to incorporate mathematical practice. And this brings something like drawings, visual elements into the focus, because those are essential for the practice to learn about new notions, to communicate ideas, but are often hidden in the end product of mathematical research as a pure mathematician, namely journal articles. And we will in particular look at ordinals, and those stands for a specific type of well-ordered thing. So you can imagine each well-ordering has one ordinal as a representant. And we will look how this idea of ordinals could be continued to the transfinite, but only focus on the very first initial segment. So all of these will be countable, so to speak. So they aren't bigger infinities, but bigger well-orderings. And now Karl will continue.
Okay, so let me start with a very, let's say, basic example, namely ways to depict omega or then even omega squared. Let's say we try it as follows. We start drawing lines, or let's say bars, where the first one corresponds to our ordinal 1, the second one to 2, and so on and so on. We do it in a way that the length of those bars is decreasing in size, in total converging to 0, and the distances between two successive bars is halving along this way. So what we obtain in this process is this first initial segment, which just corresponds to the ordinal omega. And for example, by knowing the geometric series, we know it actually fits into a finite area of the plane or the screen here. Now, to get the next first transfinite ordinal, omega plus 1, we could just start by sticking on a further bar or line on top of it, or to the right of it. We do it here in a way that the next one, the omega plus 1 ordinal, has length as long as the second bar of the first segment. And then we iterate as before. Now, 2 omega plus 1 gets now the length of the third ordinal in this picture, and so on and so on. So by iterating now this whole process, so an iteration of an iteration, what do we obtain? We actually obtain omega squared, which again is this finite representation, let's say in space, of this infinite ordinal number. But let me go on and show you something very different, namely much more symbolic in a way. Let's say we try to proceed as follows. Maybe we shouldn't write equal here, but let's say corresponds for the time being. Let's say 1 corresponds to just 1 atom, and this is very similar as in set theory. And 2 corresponds to being 2 atoms. 3 to 3, and so on. Iterating all of this, or maybe unifying this, as in set theory, we obtain the infinite ordinal omega. And then again, just we write this continuing or iterating here via this dot notation. And then the first transfinite would just correspond to sticking on 1 further atom onto it here to the right, and so on and so on. But how could we obtain from this process the ordinal omega squared? Well, by something much more axiomatic, namely by an application of the principle of replacement, actually the axiom of replacement. So what we could do is we replace each of these atoms actually by an instance of omega, which we have defined already, in total. So what we get is a sequence of all these sequences in the end corresponding to omega squared, which we can of course iterate as well. There are further examples, very different in a visual way, but we don't have time to present it in this small presentation. Thank you very much.